Hello and welcome to this practice session for CET exam. Today we will be talking about gravitation. We will be taking some typical questions from the CET exams of the past few years on gravitation, and we will solve them. In the end of the practice session, I will be talking about important concepts and formulae that are required as part of this chapter. So let's start our exam preparation right away. The important concepts that we will need as part of the CET preparation under gravitation are the universal law of gravitation, the concept of gravitational potential, the three laws of planetary motion by Kepler, and orbital mechanics. So these are the concepts that we will be using as part of this practice. Let's start with our preparation. The first question: if the distance between the Earth and the Sun reduces to 1/4 of the present value, then what happens to the length of the year on Earth? So the distance between Earth and the Sun have reduced. It is 1/4 of the present value. What happens to the length of the year? In other words, how long will it take Earth to complete one revolution around the Sun? So we will start this by using the relationship between the time period for the complete orbit and the distance of the object from the Sun. This is given by Kepler's third law. So let us start with that relationship. The relationship says that this is the relationship. The square of the time periods and the cube of the distance of the object, the orbiting object, they are proportional to each other. So the time period, the square of the time period is proportional to the cube of the distance from the Sun in this case. So remember, the distance from the Earth, between the Sun and the Earth, has reduced to 1/4 of the current value. So earlier it was R1, now it has become R1 by 4 because it has become 1/4. So let us start it that way. If the initial distance remember, we are talking about the distance between the Earth and the Sun. This is what we need to calculate. Using the relationship that I have listed here, this will be equal to and that means that the time required for the Earth in its new location to orbit the Sun has now become 1/8 of the present year. And that is the answer. Remember, we started this by using the relationship between the time period and the distance of Earth from the Sun. That's the answer to the first question. Let's go to the next question. Suppose a vertical tunnel is along the diameter of Earth. In the center of Earth, we have dug a tunnel which goes through the center of Earth, and Earth is assumed to be a sphere of uniform mass density rho. If a body of mass m is thrown into this tunnel, its acceleration at a distance y from the center. Now, if I have to draw the picture again, this is Earth. And we have a tunnel which goes right through the middle. And there is a body here. We have thrown a body into the tunnel. And that body happens to be at a distance y from the center of Earth. And we are required to calculate the acceleration of that body when it is at a distance of y from the center of Earth. So now the approach to this will be to calculate the force acting on the body when it is there, and then divide it by its mass, so we get the acceleration. So that is essentially what we're going to do. So the important thing here is to find out what force is acting on it. So what do? The force acting on it depends on the part of Earth which is here. So we take the inner part here, which has a radius of y, and that part of the Earth only is exerting a gravitational force on this object. And so the important thing now is to calculate the mass of the inner sphere of Earth. What is the mass? It is the volume multiplied by density. Remember, we are talking about only the inner sphere here. That is 4 by 3 pi y cubed, which is the volume of that sphere multiplied by the density rho, right? And that is the mass of that part of Earth. Now, using the universal law of gravitation, the force on our body is G m by y square, right? And that is equal to G into, what is the mass of Earth? Well, it is not the full Earth that we are talking about. We are talking about only a part of Earth. 4 by 3 pi y cubed rho into m by y square. And this is the force that is acting on it. So after simplifying it, but the question is about the acceleration that the body is experiencing. So the acceleration is force divided by mass that is the answer. 4 by 3 G pi y rho. So this is the correct answer. So what did we do? We calculated the mass of the part of Earth which is having a radius of y. We used the universal law of gravitation to calculate the force on the body, and then divide it by the mass of the object to get the acceleration. So that is the answer. Let's go to the next question. A geostationary orbit around the Earth has a circular radius of 36,000 kilometers. There is another spy satellite. The time period of a spy satellite orbiting a few hundred kilometers above the Earth's surface will be approximately how much? When we say geostationary satellite, it implies that the time period is 24 hours. That is the meaning of geostationary. And for the satellite to be geostationary, it has to be placed in orbit at a distance of 36,000 kilometers from the center of Earth. Only when it is at that distance, its time period will be 24 hours and it becomes geostationary. Right? Now, if a different satellite, a spy satellite, is only a few hundred kilometers above Earth's surface, then how long will it take to complete one orbit? That's the question. So it's fairly easy to do using the same equation that we used in the first question, which is the relationship between time periods and distance of the orbiting object from Earth. This is according to Kepler's third law. Now let us assume that the spy satellite, which is only a few hundred kilometers above Earth, is at a height of 300 kilometers above Earth's surface. So if this is Earth, geosynchronous or geostationary orbit is very far away. But the spy satellite is very close. So this distance is 36,000 kilometers. And this distance is much lesser. So let us assume that the spy satellite is only about 300 kilometers above Earth's surface. So this becomes 6,700 kilometers. And let's use these numbers in our formula. Remember, so R1 is, R1 is 36,000 kilometers. This is the geostationary satellite, 6,700 kilometers. What about T1? It is 24 hours because it takes 1 day to go around one complete revolution around Earth. So what we are finding out is what is T2. By substituting these values, and simplifying, you will get that T2 is approximately 2 hours. And the right answer is the third option. Again, we simply use the fact that Kepler's third law gives us the relationship between the orbital time period and the distance of the orbiting satellite from the center of Earth. That is the first thing that we used. Second thing is geostationary satellite implies, it should immediately tell you that it has a time period of 24 hours. It is not stated in the question, but geostationary means the time period is 24 hours. So using these two points, we have calculated the time period of a satellite which is much closer to the surface of Earth. So that is the answer to the third question. Let's go to the fourth question. A satellite is launched into a circular orbit of radius r, and a second satellite is launched into an orbit of radius 1.02 times r. The percentage difference in the time periods of the two satellites. So once again, we use the familiar relationship between the time period and the distance of the satellite from the center of Earth. So there are two satellites. This is Earth. So one satellite was at a distance r from the center of Earth, and another satellite was at a distance of 1.02 r from the center of Earth. So it's 2% more. So if the distance of the satellite is 2% more, what is the relationship in the time, the orbital time of the two satellites? So once again we use the relationship that T1 by T2 is equal to R1 by So this is the relationship we start with, and then we So the percentage difference from this calculation is clearly about 3%. So the answer is the fourth option. So we have used the familiar equation which relates the time period of an orbiting object to the distance of the orbiting object from the center of Earth. Moving on to the next question. When a satellite going around the Earth in a circular orbit of radius r and speed v loses some of its energy, then what happens? That's the fifth question. So there is an object or satellite which is going around Earth. It had a radius r and speed v as it was orbiting Earth in a circular orbit. It loses some of its energy. So what happens? Now the total energy of an orbiting object is given by, it's a combination of its kinetic energy and potential energy, where g is the universal constant of gravitation, m is the mass of Earth, capital M, lowercase m is the mass of the satellite, and r is the distance of the satellite from the center of Earth. Now, if it has lost some of its energy, remember the question says that it has lost some of its energy, then if you look at this expression, you will realize that R has decreased. Please remember that the total energy is a negative value. It is minus G uppercase M lowercase m by R. It's a negative value. So if that negative value has to reduce because the satellite has lost some of its energy, then it means that R has decreased. That is the first thing. What about the second thing? What about the velocity of the satellite? The orbital velocity of the satellite at any distance is given by this expression. Now, if R has decreased, then what happens to the orbital velocity? It must increase according to this equation. In this equation, if R decreases, then orbital velocity has increased. So we have concluded that if it loses some of its energy, then R decreases, which means that it comes a little bit closer to the center of Earth and its orbital velocity increases. That means that the correct option is option 4. An artificial satellite revolves around Earth in a circular orbit with a speed v. If m is the mass of the satellite, what is the total energy? So let's calculate that. You don't have to draw these diagrams when you are actually writing the exam, but these diagrams sometimes help in the explanation of the problem, which is why I'm drawing these diagrams. The satellite is orbiting with a velocity v, mass m. In that situation, the kinetic energy, the total energy is a combination of kinetic energy and potential energy. The kinetic energy is half mv square. What about the potential energy of the satellite? The potential energy is given by minus g m by r, where r is the distance of the satellite from that is r. All right. Now we have to express this thing in terms of mv square. So let's do that. So what is the orbital velocity? Orbital velocity is given by gm by r. Now if you square both sides, multiply both sides by m, right? So this is equal to this. So in our expression here, we can replace this term by where v is the orbital velocity. So the total energy the second option is the answer. So what did we do here? We basically calculated the total energy as the sum of kinetic energy and potential energy. The potential energy is minus gmm by r, which we wrote in terms of mv square. And when you add the two components up, the potential energy and the kinetic energy, the sum is minus half mv square. And the second option is the answer. Let's go to the 7th question in our practice paper. A particle is fired vertically upward from Earth's surface, and it goes up to a maximum height of 6,400 kilometers above Earth's surface. Find the initial speed of the particle. Now, you have to read it carefully and realize that the radius of Earth is 6,400 kilometers. This object was fired vertically upward, and it went to a height of 6,400 kilometers above Earth's surface. So if you were to draw a diagram, this is the radius of Earth. And the object was fired from here. And how far did it go? It went high. How high did it go? It went another 6,400 kilometers above Earth's surface. Right? So that is also equal to r. And r is the radius of Earth. So what do we do? When it was fired from here, that is the first position. It reached the maximum height, that is the second position. At the first position, it has Ke, which is kinetic energy, and P, which is potential energy. Right? At the second point, it has potential energy, but kinetic energy is equal to 0 because it reaches that height and starts falling back to the Earth. At its highest point, its velocity is 0. Therefore, its kinetic energy is 0. So this is the principle we will use to find the answer. So the potential energy at 1 plus kinetic energy at 1 is equal to potential energy at 2. there is no kinetic energy at point 2, remember, right? So minus gmm by r plus half mv square is equal to minus gmm by. Now, how high does the object go from the center of Earth? It has gone to a distance of r from the surface of Earth. So, from the center of Earth, its distance is 2r. And when you solve this for v, of course, m gets cancelled, and we use the value of g to be 6.67 into 10 to the power of minus 11, and the units are meter cubed per kg second square, and the mass of Earth is 6.4 into 10 to the power of 24 kgs, and the radius of Earth is 6,400 kilometers, which is 6.4 into 10 to the power of 6 meters. So using all of these values and solving for v, you get and this is the correct option. So what have we used in this question? We have used the conservation of energy. When the object is launched from the surface of Earth, it has potential energy and kinetic energy. When it reaches its highest point and it is about to fall back to the Earth, it has potential energy but zero kinetic energy. And that is how we get this equation. And then the potential energy is given by gmm by r and the kinetic energy by half mv square. The value we are trying to find out is v, the velocity. And when you solve for v, you get 7.9 kilometers per second. The eighth question. A satellite of mass m is moving around Earth in a circular orbit of radius r with a constant speed v. The work done by the gravitational force in moving the satellite in the first quarter of the orbit. Now this is a question that you have to understand very carefully. Once again, let's start with a simple diagram. The mass is m, the velocity is v. It is a circular orbit of radius r from the center of Earth. Now, at any point, the velocity of the satellite is in this direction. And the force exerted by Earth, the gravitational force on the satellite, is towards the center of Earth. Now, if I use a different color to illustrate the force of gravity, the force of gravity is along the blue arrow, and its instantaneous velocity, its movement is always perpendicular to the force of gravity. So this is always 90 degrees, right? The instantaneous velocity is tangential to its circular orbit. So we know that work is equal to, right? And when the angle between the force and the displacement happen to be 90 degrees, work is not done. So the only force acting on this satellite is the force of gravitation. But its displacement is constantly perpendicular to the force exerted on it. So there is no work done by the gravitational force in moving the satellite. The potential energy or the kinetic energy of the satellite does not change. So no extra work is being done on the satellite. So work done by the gravitational force is zero. Remember, there is only one force acting on the gravity, on the satellite, and that is perpendicular to its instantaneous velocity. So work cannot be done by a force which is perpendicular to the direction of displacement. So the work done is 0. Ninth question. Weightlessness experienced by an astronaut in a satellite orbiting Earth is due to what reason? You must have all seen videos where astronauts are floating in a satellite as the satellite orbits Earth. Why do they feel weightlessness? That's the question. So any object which is orbiting Earth has an instantaneous velocity v, and it is orbiting Earth at a distance of r from the center of Earth. Now anybody who is there experiences, of course, there is a force of gravity that is exerted because of Earth, and we call that weight. But anybody who is inside the satellite, will also experience a force because of the inertia. And what is that force called? That force is called inertial force. It is also known as centrifugal. And this is only experienced when you are in the satellite. You are inside the non-inertial reference frame. So there is an inertial centrifugal force acting away from the center and the weight acting towards the center. Now these two are equal and opposite, and that is why the astronaut feels weightless. The answer is this one. Why do we call the centrifugal force a pseudo force? Because it is an inertial force. There is no outside agency which is exerting the force on the astronaut. It is caused because of inertia, and it can only be experienced in the satellite, in the non-inertial reference frame. So it's a pseudo force, centrifugal force. So the centrifugal force is balancing the weight of the astronaut, and that causes a sense of weightlessness. Next question in our practice paper, the 10th question is, a projectile is fired vertically upwards from the surface of Earth with speed equal to half the escape velocity. The maximum height reached by the object above the surface of Earth. Now, if it were fired with a speed equal to escape velocity, it would escape Earth's gravity and go away. But it has not been fired with speed equal to escape velocity. It has been fired with speed equal to half the escape velocity. So how high does it go is the question. Now the escape velocity at any point is given by So what is the velocity with which the object has been fired? It has not been fired with escape velocity. It has been fired with half the escape velocity. Right? Half. Now, how high does it go? We will again use the principles of conservation of energy. At the surface of Earth, the projectile has kinetic energy and potential energy. At its highest point, it has only potential energy. Kinetic energy becomes 0. So we will write that same equation, and then we have to solve for how high it goes. So the potential energy on the surface of Earth is R. This is the radius of Earth because it has been launched from the surface of Earth. It also has kinetic energy when it is launched, is equal to minus gmm by R. Right? Now, what are we trying to find out? We are trying to calculate how high it goes. We are trying to calculate small r, right? Now, what was the kinetic energy at the bottom of its journey? The kinetic energy when the projectile is launched right? So we use this value here and we continue with this side of the calculation. So these three get cancelled right away, right? And you have to calculate the relationship between r, small r, and the radius of Earth. And when you simplify this, you will get what does it mean? It has reached a maximum height which is 4 by 3 times the radius of Earth. So the question here is, how high above the surface of Earth did this object reach? So the height one by 3 RE. That is this. That is the answer to the question. We have used the principle of conservation of energy. At the point where the projectile is launched, it has potential energy and kinetic energy. At the highest point, it has only potential energy. And that is what we use to calculate how high the object goes. So this was our practice paper. Let us look at some of the important things that you will have to remember in order to solve questions from this chapter on gravitation. The first one is Newton's universal law of gravitation, where the force F is given by Gmm by r square. This is the force of attraction existing between two objects, one with mass capital M, one with mass small m, when they are at a distance of r from each other. The force is given by this equation. And G is, of course, the universal law of gravitation. The second important thing to remember is something called orbital velocity. If you have Earth here, and there is a satellite which is orbiting Earth at a distance of r, then we can calculate the orbital velocity by equating the gravitational force between the two to the centripetal force that the satellite will be experiencing. So essentially we start off by saying that the gravitational force is equal to the centripetal force, and by cancelling and solving for v, it becomes the orbital velocity, and that is equal to the orbital velocity at any distance r from the center of Earth. Notice that it does not depend on the mass of the satellite. A third important relationship is the escape velocity. This, of course, is the orbital velocity. At this velocity, it continues to orbit the Earth in a circular orbit. Escape velocity means that it will escape Earth's gravity, will be more than orbital velocity, right? Root 2 times. This is an important relationship. So So it will be at any distance r from the center of Earth, this is the orbital velocity and this is the escape velocity. The third one, or the fourth important point, is the energy It consists of both kinetic energy and potential energy. And the kinetic energy is given by half mv square, and the potential energy is given by, and when you add them up and replace mv square in terms of g, m and m, you will get this is the total energy of the satellite which is orbiting Earth. And the last point that we used in several questions in today's paper was the relationship between the time period and the orbital distance. And this is given by Kepler's third law, stating that t square is proportional to r cubed. So these were some of the important concepts that we used in the questions that we answered today. I hope you found it useful. Prepare well for CET. Good luck.